Good morning, guys, and welcome back to Dynamics course. In this lecture, we're gonna start a new chapter, chapter 14 in the textbook, and it's about uh, uh, always the kinetics of particle, but now it's about the work and energy. So, guys, previously we talked about the forces causing an accelerated motion, and we applied the Newton's second law. Now, in this chapter, we're gonna apply the principle of work and energy. So what is a work? What is an energy? What's the difference between kinetic energy and potential energy? And how can I apply the work in order to find some variables? And what is the principle of work and energy to a particle or system of particles? So this is about the chapter 14, and in fact, in this chapter, we are going to acquire knowledge that can allow us to, for example, design the track of a roller coaster, design the height, the radius of curvature in order to control the forces experienced by the passengers. And don't forget, guys, that any roller coaster has some values, and this is designed in order to have some high speeds. All right, in order to reach some high speeds. So we're gonna see how, and we are also going to discover why crash barrels are often used along roadways. So do you know why? In fact, they are for the crash protection because they absorb the car's kinetic energy by doing a certain deformation. So guys, if I start analytically, I know that the Newton's second law states that F is equal to ma. And I'm going to start from this equation to formulate the equation of work or the principle of work. In fact, guys, I'm not going to use a is equal to dv over dt, although I'm going to use it in the next chapter. But in this chapter, I'm not going to use this equation. I'm going to choose another equation, which is the independent equation of time. So I know, guys, from the independent equation of time for kinematics, that A ds is equal to v dv. So I know, guys, that A ds is equal to v dv, and this is the independent equation of time that is used in a general rectilinear motion. Now, if I'm going to use this equation in curvilinear motion, what I should modify is this acceleration right here. I should use the tangential acceleration because I know that the tangential acceleration stands for the change in speed, right? So here, since I mean by this A, the change of speed, then I can use ATDS if this is a curvilinear motion or ADS if this is a rectilinear motion. So I know that ATDS is equal to VdV, and this means, guys, that AD is equal to VdV over ds. What I'm gonna do now is to replace this A in rectilinear motion by v dv over ds, or this at in curvilinear motion by v dv over ds, to generate the principle of work. So if I do this, if I replace this at by v dv over ds, and then I take this ds to the side of f, and then I apply it as an integration between s1 and s2. So if I do the integration and then I do the sum, because I may have more than one force, all right? So I know from the second law that sum of forces equal to mv dv over ds because it is equal to ma. Then if I do the integration, because this is a differential equation between s1 and s2, I'm gonna have this formula. The integration of the sum of forces, or the sum of the integration of the force ds, is equal to the integration of mv dv. And I know, guys, that the mass m is constant, so I can take out this math from the integration, and then I know that the integration of v dv is nothing but half v squared 2 minus v squared 1. So I'm going to have that the second side of the equal sign, or the right side of the equal sign, is equal to half mv squared 2, or half mv squared on position 2 minus half mv squared at position 1. Now guys, I'm gonna take a look on this equation right here and I'm gonna analyze my finding. First of all, what is half mv squared? What is the a quantity that is equal to half mv squared? This is what? This is in fact the kinetic energy. So it is an energy and it is related to the velocity. This is the kinetic energy. In French, l'énergie cinétique. Now this kinetic energy is represented by T, all right? So in English, the symbol of kinetic energy is T, and it could also be represented by Ke. All right, guys? Now, in French, the symbol is EC. So now you have to change your symbols a little bit. In English, they are T or KE. What does this mean? This means, guys, that this integration here is equal to the difference of kinetic energy between two positions. This is called the work, all right? So the work or the sum of work of all the forces exerted on this particle is equal to T2 minus T1. Physically, the work of a force is the energy transferred to this particle by doing a displacement caused by this force. So the work is also an energy. It is called a work because this is the work of a force. If this force has a work, then this force will do some displacement. So this is, guys, the definition physically of the work. And now we know that from the principle of the work, that this work is equal to the difference of kinetic energy. Which work? The sum of work of all the forces exerted on this particle. And guys, you have to know that this work could be negative. Why? Because in fact, this kinetic energy could be decreasing. I know that the kinetic energy is always positive because in fact it is equal to half mass times v squared. The mass is always positive. The velocity could be negative, but since it is squared, then it should be positive. And this means, guys, that the kinetic energy is always positive at any position. However, this kinetic energy could be decreased because it could be exchanged by some other form of energy, like the potential energy. For example, if I take again the roller coaster example, if I'm gonna climb here this height, the kinetic energy will decrease, my velocity will decrease. And then I'm gonna reach the top where I can have a zero velocity. And in this case, guys, the kinetic energy is decreasing because it is exchanged by the potential energy, right? Now, in this case, the work of my forces will be equal to a negative value. If I don't do any displacement in the same direction of a force exerted on this particle, then this force is not doing any work. So guys, in fact, if this force is not doing any displacement, then as if it is not presented. In this case, the work done by this force will be equal to zero. So this is, guys, the principle of work and energy, and what you have to know, and this is good news in fact, is that this principle of work given by this equation, the the kinetic energy at position 1 plus the sum of work done by the forces exerted on this particle is equal to the kinetic energy at position 2, or in other words, the sum of work done by the forces exerted on this particle is equal to the difference of kinetic energy. This principle of work equation is not a vector equation. So it's not a vector. It is a scalar equation. Because in fact, the kinetic is given as half mv squared. And I know that any vector squared will be a value. So this is good news. But how can I say that the work is a scalar value? So what is the general equation of the work? What should I know about the general equation of the work? I know for now that it is a scalar value. Alright, what does this mean? How can I find the work? What is the general equation of the work? When this work is negative, when it is positive, and when it is zero? In fact, guys, by definition, the work is defined as the product of a force and the displacement components acting in the same direction of this force. Because I know, in fact, that a force does a work on a particle when this particle undergoes a displacement along the line of action of this force. Which means, if this force does not do any displacement on its line of action, then this means that there is no work. This force is not doing any work. If I take this general equation, this general case here, I have a path S, and I know, guys, that there is a force F on this position S, and at this time I have a displacement ds, which is the scalar value of the vector dr. What is dr? It is the vector displacement, and it's equal to the position r prime minus r. Alright, if I do the projection of dr or of ds on F. So if I do this projection, how to do the projection? Of course, to take a perpendicular line. Then this projection here times the force F will be equal to my work. So in fact, the work is equal to the force exerted times the projection of ds on this force. And since I am saying ds, then I'm gonna say here dw or du. In English, the symbol of work is U, alright? Because this is an energy, and U is usually the symbol of energy, and to not get confused between the weight and the work, alright? So I'm gonna say this is du, alright? So du is equal to F times the projection of ds, the displacement, on the force F. This is du. And that's why it is a scalar value. That's why, guys, I said in the slide that the principle of work and energy equation is not a vector equation. Instead, it is a scalar equation. Du is equal to what, guys? Remember? What is F times the projection of ds over F? It is F ds cosine the angle between them, which is what, in fact? It is F dot dr. So guys, it is the scalar product of the force F with the displacement vector.